This presentation is from the 2012 Hollywood Post Alliance Tech Retreat, at which I presented this model for the second time in 5 years. The pricing is current as of mid-2012. I am Dave Kavanaugh. I was IBM's Global Services Digital Cinema Services Delivery Project Executive for many years, where my teams built the WB, ET's Digital Library and Archive, and other projects, including a model for archiving digital content for a Warner's business unit. I was Movie Beam Program Manager at Disney for its development and initial release, Project Director for the development of Blueprint at Sony Pictures, and Sun Microsystems Digital Cinema Lead when Jerry Pierce of Universal asked me to stop talking about archiving and figure out a model for which he provided the initial numbers. So let's talk about archiving. Longevity, accuracy, cost. I have found these three topics to be the major areas of resistance to digital archiving. Longevity. Film meets this goal because it has been static for over a century and seems to be a good physical carrier. Digital will never be static. Digital store and ignore is not an immediate issue. It's an accessibility issue having nothing to do with the survival of the bits. So film is traditional for archiving. But what are we archiving? The archive is the only part of the workflow that has not been digitized. We are archiving exactly what we don't shoot, edit, post, exhibit, repurpose, store in the library, download, or stream. As Leon Silverman pointed out in his opening remarks at JTS 2004, the data is the master record. Will film really last? We already know it warps and shrinks and fades and cracks. Film is a physical carrier, a polymer. Mark Ritchie noted in Kinema in 1995, all polymers decay. Dan Rosen raised an excellent point in 2007 regarding the loss of analog process expertise. Regardless of our wishes, this expertise is dwindling, and that, more than any technology preference, must be considered when discussing an archive life of centuries or millennia. In a perfect archive, the content would be retained forever, accurately and accessibly, and inexpensively. The content would not be subject to fading, shrinking, warping, dust, dirt, scratches. In short, it would not be subject to the vagaries of the physical world. A story, a movie, is an ephemeral event. Locking it to the physical world seems antithetical, especially if mature technology exists, allowing disintermediation. Archived content is useful only if it doesn't change, if the content retains its accuracy. To say that digital hardware and software technology change often seems an understatement in the timeframes of an archive. The 3-strip YCM process was created because color film fades. Registration issues can occur when recombining older YCMs. Generational losses do occur. In a digital archive, registration is not an issue. It's irrelevant. So are dust, dirt, scratches, and color fade, and there is no generational loss. Discussing data accuracy requires discussing the concept of a managed archive and managed migration, which raise the issue of a rules-based software archive manager. A digital content archive without an automated management system is not an archive. It's a computer storing data, not a system archiving digital objects. The model presented here, and it is only a model and only one of many, is based on an automated, rules-based software archive management system and automated computer tape libraries. Tape is inexpensive, proven technology, significantly automated, and when tape is replaced, it is likely the replacement will be similar in price point and automation due to the sheer numbers of robotic libraries and the exabytes they contain across the IT world. This model has 2 copies of each movie in each of 2 geographically separated libraries, or 4 copies total. If EMP is a worry, one of these easily could be put underground at current film vault facilities. The model presented here is based on Sun Storage Tech, now Oracle technology, for 2 simple reasons. I was working at Sun when it was developed. The Software Application Storage Archive Manager, SAM, is a true archive software application and can do all of the things required of it in this model. I'm unaware of any similar system. The model is vendor independent. Let's talk first about hardware accuracy. Are the bits in the digital system still the right bits? Can they still be read? Nothing in this model is new. Everything is commercial off the shelf. Error correction code, ECC, is and has been the standard accuracy methodology for data on tape for decades. ECC are probability metrics of bit error rates and come in 2 flavors. ECC undetected, I lost a bit and don't know it, and ECC uncorrected. I lost a bit, I know I lost a bit, and I can't correct the bit I lost. Oracle Storage Tech Sun publishes an undetected bit error rate of 10 to the minus 33. This is the probability that the loss of 1 bit may not be detected. 4 copies of the archived object equals 10 to the minus 132. IBM does not publish this metric. Storage Tech publishes an uncorrected bit error rate of 10 to the minus 19. 4 copies equals 10 to the minus 76. IBM's L2O library is 10 to the minus 17 or 10 to the minus 68, same neighborhood. These all are based on best practices for digital archiving. A feature, a DCDM, is roughly speaking about 10 terabytes. 10 to the 13th bytes are roughly 10 to the 14th bits. With trims and outs, we may want to archive a 20 terabyte object. At the other end of the size spectrum, one can make the case that an archive object may be 100 terabytes or even more. Both are priced in this model. A 10 to the minus 76 loss probability on a 20 terabyte object means 1 bit loss in 2 times 10 to the 62nd movies. A model using a 100 terabyte archive object size probabilistically would lose 1 bit in 10 to the 61st movies. In this model, we throw away every server and every disk subsystem every 5 years, every tape cartridge every 5 years minimum, and every bit on every tape is automatically audited every 6 months, and a copy will be replaced if the audit fails on any bit of that copy. Every tape library is replaced every 20 years. Who knows how many times the software will have been changed during the duration of this model? More on software in a moment. The point is that we have a minimum of 20 generations of migration and an arguable maximum of 200 in the course of a century, the duration on which the financials for this model are based. As you know, generational film loss is real. What is the generational impact on the algorithmic bit error rate in a digital archive? For our purposes, it doesn't matter. In probability, 1 is perfect. Any given read of 1 copy of 4 has a probability of loss of 1 minus 10 to the minus 19. That's pretty close to 1. The probability it will fail 1 or more times during n axes is 1 minus the probability it will succeed n times in a row. For n less than 10 to the 19, this basically is n times 10 to the minus 19. Suppose over the course of the century of this model that the archived object is accessed, read, and written 1,000 times, or 10 times per year. The chance of an uncorrectable bit error in 1,000 accesses is 10 to the minus 16 for 1 copy. But our model has 4 copies. The chance of 1 bit being lost and not corrected in 10 to the 3rd read-writes in 4 copies is 2 times 10 to the minus 59 for a 20 terabyte DCDM, 10 to the minus 58 if the archive object is 100 terabytes. Other standard algorithms and methodologies exist that make the loss of a single bit even more difficult to conceive. SHA-256 is one of those models. Voting bit by bit is another. One also can take a 10 terabyte object, make 41 terabyte files from it, and 31 of those 40 would need to be lost to preclude perfect recreation of the original file. I know this sounds fanciful to those who have been unable to read a file 6 months later, and I am aware that many of us never use read after write, so the data may not have been there 6 seconds later. Nor do we always use brand new tapes. Let's use the term software reliability for the changes to the file format, application software, and operating system. Does the software accessing the archived content change too often to be reliable? Remember, we automatically audit every bit of every copy of every object every 6 months. If the file format or application or operating system necessary to read the archived object has changed, then during this audit that file can be read in the format in which it was written and rewritten in the new format with the new application under the new operating system, as long as this is done contemporaneously. In this software conversion, the image file itself is not altered, only the wrapper. We can archive accurately forever. So let's talk about cost. This model is a conservative pricing model. List pricing, no depreciation, no salvage costs, including hardware, software, maintenance, and media. And we've added 150% above the price of everything for labor, floor space, and electricity, an average of $728,000 per year if the object archive is 20 terabytes, and an average of $826,000 per year if the object being archived is 100 terabytes. I'll also show a 200% uplift model. The model is based on a single studio, 20 features per year for 100 years. No television, sports, news, or documentaries. Because of scaling, adding these would drive down the costs. This also may well be the most expensive model possible. Others are less expensive. These are the film costs I was given by the studios when developing this model in 2007. I assume they have changed, but also that the change, either up or down or both, is not large enough to be material to this order of magnitude discussion. And the point of this discussion is just to present a model. If I'm wrong, I'm happy to be re-educated. Per this information, the cost to archive a single feature on film for 1 century, including the YCMs, color match print, storage costs, etc., is around $130,000. These are the digital costs. A 100 terabyte object with a 150% uplift costs $75,000 over the 100-year archive. The uplift amount is about $826,000 per year. 100 terabytes at 200% is $83,000 with an annual uplift of $1.1 million. I recently presented this to a major studio technical executive. His view was that the 100 terabytes is too large. That ought to be more like 20 to 25 terabytes. You can see those numbers. Here is the comparison. 100 terabyte object, 150% uplift, 1 studio, 100 years. This is what it looks like over time. This is the $130,000 Century film cost. This does not scale. And this Century to date cost of the film archive growing at 20 features annually. This is the cost of the digital archive object over the century. This does scale. And the Century to date cost of the digital archive. Here is a 200% uplift, 100 terabytes, etc. And an observation. A digital archive has 3 redundant copies of the object archived, or more, as many as you want. A film archive has 0 redundancy. Based on that, your insurance company may pay for the archive. 20 terabytes, 150%. And the graph. And 20 terabytes at 200%. But why are we archiving this content? To repurpose it, the long tail. Well, repurposing from YCMs back to the editing system, I am told by studios, cost $65,000, and misalignment and generational loss issues arise. If we do it from digital, for a 100 terabyte object on 5 terabyte cartridges, about $7,000, and it is perfect. So if we were to repurpose each movie in this archive only one time in the century, the costs look like this, for one studio. If we put that into a bar chart, the comparative costs are easily illustrated. This pie chart illustrates cost by budget items. Longevity, accuracy, cost. Let's look briefly at the impact of static archiving of digital content. Let's assume a perfect digital archive medium. Bit-perfect storage of bits for archive durations, a store and ignore paradigm for content stored digitally. What does a digital system require in order to read the bits stored? In order to read those bits, we will need the source code of the program that wrote them, the operating system on which that source code runs or can be made to run, the compiler to compile that source code to create the object code. These all are code elements that can be saved as source code for the future. But are they really useful in 100 years? Will we really have usable compiler and object code needed to read those bits and read that content? Because the digital food chain requires 2 other items. In addition to the elements already listed, we'll also need the chip and the interpreter that generated the executable. The compiler and object code are specific to that chip and interpreter. Does anyone think we'll have, in 100 or more years, the chips and interpreters available today? Because all current static digital archive proposals, except DOTS, are reliant on that answer. And the post-production community's answer is no. At the HPA Tech Retreat in 2012, Jerry Pierce asked the audience at the end of day 2 how many thought that a perfectly preserved bit-perfect JPEG file would be readable in 50 years. Only 8 of over 150 people raised their hands. Going forward, archives will be managed, not static. We will not have that chip, and the instruction sets for chips will have changed so drastically by then that it will not be able to be successfully emulated. Not in a century, certainly not in a millennium. We may be able to store bits perfectly forever on these new media, but we will not be able to read them from a static archive. Take an 8.5-inch single-sided diskette, 128K from 1980. The bits may be perfect. Can you read it? That's only 40 years. Take a WordPerfect document on a 3.5-inch floppy from 10 years ago. Even if the bits are perfect, and they probably are, can you read it? No. The entire concept of a static archive, of store and ignore, is irrelevant for digital technology. But I have shown how in a managed archive, not only can the content be archived successfully, accurately, literally forever, but that this can be done with commercial off-the-shelf technology today and at a cost far lower than that of film. Let's look briefly at the financial comparison. These are the assumptions in this model. They are standard and fairly conservative. This is the breakdown of cost and comparisons at intervals of 1, 3, 10, 25, 50, 75, and 100 years. As you can see, a managed digital archive becomes less expensive than the traditional film archive in year 3. And remember, there are 4 copies in the digital archive of those irreplaceable assets. So that's it. Archiving content digitally. More accurate, disintermediated from the physical deterioration, nearly perfect, nearly forever. I have shown a model, and it is only that, in which content can be stored accurately and longer than film, literally forever. This model, and others, can provide for a more accurate repurposing of content than can film, and it is less expensive than film. In closing, however, I'd note that of everything I have presented, Dan Rosen's comment is the most important. Put aside the technology, put aside this entire model, put aside any particular digital model. Traditional analog methods of archiving cannot keep up with the loss of analog process expertise. As in any area of progress, the loss of human expertise of the traditional methods will force changes we may or may not want to accept. It's just good to know that those changes will result in a longer lasting, more accurate, less expensive content archive. Thank you.